Okay, it's 3:45. We should start the Matplotlib session now. So I'll stop sharing my waiting slide and you can start sharing your screen.
Okay. Are we online already or?
Yes.
Oh, okay, great. So this is a Matplotlib introduction. This is a joint session, so Max will also jump in and show a really cool thing, how to create PGF plots or really cool plots which integrate into your LaTeX environment with Matplotlib. So I will first do the introduction and then change the chair. So let me create a new notebook. So you can do a git pull again. I hope there's this, yeah, so I just created the pull request like 15 minutes ago. I'm sorry, I was a bit late with that, but you can just follow along and look at the data, the notebook later on. So let's start with the basics. Let me write Matplotlib at the top so that we know what we're doing here. Matplotlib and my versions are here, and my random number generator is initialized with 42, meaning of life, as always. So let's get started with Matplotlib. So I think the best way to learn Matplotlib is to explore the gallery, as I already pointed out today in the morning. If you were connected, let me show it to you very quickly. So you can do this. You can go to examples and then scroll through these example section, and whatever you click on, for example, if you want to generate your barcode for whatever reason, you can just usually take this and paste it in a cell and execute it, and this will work out of the box. So it's really nice to just explore how things work. As I already pointed out, it's sometimes not the best way to do things, or not the recommended way, but most of the time it's really nice, and it gives you some really a good starting point. Nevertheless, I think that some basic functionalities should be explained, and I wish I had this little course, which will only take a few minutes, I hope, or half an hour, to get the feeling of how to work with Matplotlib in the first place, because I did many things wrong in the beginning, and this several years ago, because I'm old. All right, let's start off with an n equals 100, as always, I feel like, and create a linspace from 0 to 2 times pi, so 100 samples of that, and this will be our x's values, and our y's values. I would like to use the sync function. I like it. So this is how our x's look like now. So we have created equidistant values between 0 and 2 pi, and the y's are looking like this. I can delete them because it's not needed. You have seen it, and let's create a plot. So the very first thing you have noticed is very often you import the global thing, which is this PAT. So you often see something like import Matplotlib pyplot as PAT, and this is then pyplot with a T again with another T, this T. So this PAT you can then use to as a factory to create all your stuff. So it can also be abused, I would say abused, to do the plotting very quickly. X's and Y's like this. X's. I'm getting a bit tired, I guess. Okay, so this will give you a plot, but you don't have any nice handle to alter the plot in this case. So you don't get back a variable name, which you can then work on. But you can do some things like title and then set the sync or whatever, and this will work. But the problem is that this is altering the global things behind the scenes, so it's not really the recommended way. I would always recommend to use the the other way, where you create your own objects and then use them. So, for example, you can use PRT figure. This will create a figure for you. You can see that it has a specific size, and this well, it doesn't do anything fancy yet. But to this figure, you can now add an axis, and you do this by calling the addAxis method, and you tell it the parameters. This is the basically left and bottom, and then width and the height. So in this case, we added this X to the figure, and we also got back a reference so we can use it now. If I now hit fig, then you can see that it already is something which starts to look like a plot. And now I can use this X object, which I created before, which is attached to this figure, to create a set of points. For example, I can use the scatter function. Again, I can hit Shift Tab to see what kind of parameters I can pass in. But for now, I just go ahead and add these X's and Y's and put a label on, for example, sensor Q. Okay, so I added this. So this means that now this X has received a set of points containing made from these data sets. So if I look at my figure now, it looks like this. And you can here also see the sampling of this function. Yeah, we are starting to compose things. You can also add another axis to this thing by calling again fig axis. And now we specify another position. So for example, 0.5, 0.5, which means it's the middle of this plot. So again, it's starting from it's left bottom. So 0.5 will be here, from the bottom, 0.5 here, and then the width in percentage of the figure, 0.4, 0.4, for example. This is our sub X. And now let's plot something on it. So sub X plot. Plot again the axis, and then let's call the sine function. And yeah, we can also do some other cosmetics, like setting the color, adding a label. And let's say this is coming from sensor P, and add another one because you can add multiple lines to a single axis. And P, yeah, do again sine axis. And let's multiply it by 0.9 so that it looks a bit different. Color, you can use many names for these colors, like steam blue, lime, red, black, or many complicated ones, or also hex values. You can also define different line styles, which I will do now. For example, minus dot will get a dash dotted line, and I will add the label to it called lower upper, so like this. So this now adds 2 lines to it. You don't see what happened right now because it always just returns the last statement, basically, and this will not trigger the display in this notebook. But if I hit Shift Enter with a fig inside the cell, you can see that we now added this these 2 lines. So this is already something quite common. So you can nest plots in each other, and these are the basic building blocks of putting things. Now you might want to add some labels to it. And for this, so remember, our X object is this outer one. So this where this blue line is displayed, or the sync function is displayed, and this sub X is this other plot, which is displayed here on the top right. So if I now take this X object and to set X label, I can set it, for example, to time, and set the Y label to voltage and millivolts. Voltage, like this. Okay. And let's have a look at how it looks right now. So you can see, you now have this X-axis and Y-axis annotated. And let's also annotate the sub-axis. So sub-X, set X label to time, as again, and sub x set y label to, and now we can use some cool thing. This is a raw string in Python, so this means that whatever you put inside with escape characters, it will be not interpreted. So I can here now use LaTeX expressions. So those are wrapped inside these dollar values like this. If you want to use special characters, and if I now hit enter and look at the figure, you can see that this mu actually rendered via a LaTeX engine behind the scenes to an actual mu. So now we have added access labels to our subplot. And okay, let's also add a legend. So to add the legend, you can call the legend function on your axis. If we call it on the x, then we will get a legend on the main figure, on the bigger one, like you can see here. So now everything which was added with a label is now displayed here in a box. And let's do this also for the sub-x. So as you remember, in our sub-x, we added 2 entries. So this corresponds to 2 lines with 2 different labels. So if I do this sub-x legend and look at our updated plot now, it will now show both of them, both of the labels with the right markers and line styles and colors, etc. What you often want to do is something like indicating a line or a threshold or something like this. Those are really nice features. You can add them using the XH line or XV line. So let's add an XH line at the position 0.15 or so with the line style. Let's try a different one, for example, this one. And now use as a color some hex color, something dark and bluish or so. Let's do it like this. So this will now add a horizontal line at 0.15. So this should be somewhere here with this line style. Let's have a look at the figure, how it looks like now. And indeed, we have now this line added. Yeah, maybe you want to add another horizontal line. So I now define some time points, time of interest. I call it TOI in this case. Let's save it in a variable so we can reuse it. And we define some options for our vertical line with a dictionary again. This trick I often use if I use the same style over and over again. So for example, if I want to use the line style with the dash, and the color should be deep sky blue because this is so nice, and the line width should be 2. And these are my options now. And then I call this XV line with the point of interest and this time point which we created before. And then we do this dictionary expansion. So this will basically expand and it will be turned into line star equals, etc., comma, color equals deep sky blue, etc., etc. So just in case you don't know how this double asterisk works, this is what it will do. And we put it also on the sub-axis. So we want to use the same XV line in both plots, TY, the ops. And let's have a look at the figure. So as you can see, now we have this lines added. And yeah, there are also grids which you can activate. This is also a very commonly used thing. You just call grid. Let's do some gray thing. And for the sub-X grid, we use a color. Let's do something like slate gray or so. So now we have added 2 different grids to both plots. Yeah, it's starting to look good, but I think that the font size, at least for the upper, for the outer plot, is quite small. There's also something which you want to set quite often. So I can do here something like iterating over the axis. So this is just a simple Python loop over the x-axis and the sub-x-axis. I could also write it out, but I think it's nicer if I do it in a tiny for loop. So what you can do here is you can call label and then set font size do 20, for example. And there is axis. And did I make a mistake late? Sub-x. Oh, x-axis, y-axis, like this. Okay, figure. It didn't work very nicely. Let's try it again. Oh, yeah, okay. It's doing the wrong thing. Yeah, I wanted to set only the outer ones, right? Like this. Okay. Yeah, it's a little bit like this. It's a nice mistake. You can see that you can access these in the same way, whatever axis they are. Okay. Maybe you want to reposition a plot afterwards. This is also something which might be of interest. So you can access this sub-x in your figure and call the set position function. So for example, you can relocate it to be positioned at a different left and bottom coordinate and different width and height. So if you want to adjust it to look it nicer for your final presentation or so, you can do it like this. So here you can see we now made it a bit bigger compared to this one. So this is how it works basically. And last but not least, I wanted to also include some SciPy things. So this is the only thing I could come up with very quickly. I import SciPy signal and I use this SciPy signal find peaks TWT. Don't bother about the parameters. This is a peak finder, which is very nice and configurable. And in this case, I have to pass in some values so that it works nicely. It finds the peaks of my original signal, which are the y values of this sync function. So you can use this to do this scatter, and then you access your original axis array. You put in the peak index and your original y's array and put in the peak index. And let's choose a color of red, and the marker I would like to use X and make it really big, like 200 or so. So let's have a look how our plot looks like now. And as you can see, yeah, there's a lot of things you can tweak about this peak finder, but it's already not so bad. So it found the peaks of our sync. Okay, it looks a bit ugly now, but I think it kind of shows the concept of how you can work to make your plot in a modular way. If you want to save it, you can call save fig and then just provide it a name like plot PDF or so. If you choose PDF, it will save a vector version. If you use a rasterized format like PNG or GIF or whatever, then it will save it in the right one. So one thing which you most likely want to pass in is this bbox inches tight. This will make sure that things are not cut off. So yeah, in this case, I created this plot. Let's go to this folder, Matplotlib plot, and there you can see is our PDF file containing our final plot. Okay, so before I pass over to Max, I would like to make your life a little bit easier because creating these fig-x, etc. manually might be a bit tedious. There is this function which I already used in the numbers, in the pandas lecture, which is this subplots function. So this will actually create for you a figure and an axis. It can also create multiple ones. So if I do fig axis equals PLT subplots and then rows equals 2 and then cols equals 3, for example, then you already have this nice evenly spaced thing. So you don't have to care about where to position them, what is the left and bottom coordinate, what is the width, etc. So everything is done for you. And keep in mind that this is now an array. It's basically, if you look at the D type, or the type, you can see that it's a NumPy array. So it abuses NumPy for this. It has a D-type object. So it's structured like this, and you can access the first subarray like this, and the first element of the first subarray like this. I'm sorry. Let me copy this so that everything has a trace. And this way you can work with it. So if I do something like axis, actually you can also do it like this. This is the same instead of doing this double thing. So I can choose the axis in the first line and the third one, and scatter, for example, my cosine function or so. So if I look at my figure now, you can see that I added this cosine function into this this exact plot. And what you also can do, if you don't want to bother about which column you are, but just iterate through it, is you can flatten this axis array. And for example, like this. So axis flat will give you, maybe I should do first. Let's expand this generator. So this will flatten it. It's basically a reshape of this NumPy array, which makes it a flat list. So if I do this, then it will access the fifth element. So this will be the 0, 1, 2, 3, 4. This one in the middle would be then our axis. So yeah, let's scatter our sync function again. This, and have a look at the figure. So you can see that now we added our function. And what you have seen in my previous presentations is that I often iterate through the axes and add them. So I thought I would show you some example of it. I create a color map. So there is this color map utility functions which you can use to create all kinds of color arrays for later use. So here I used those should be always between 0 and 1. And the length should be now the length of axis flat, or you can also use the size if you want to. So now I created 10 color values with the Viridis color map. So these are RGB and A values, so red, green, blue, and transparency. And I can use these colors now to color my plots if I do this iteration. So for example, for a given function and axis and color in, let's zip them together in NumPy cos, NumPy sine, NumPy sync, NumPy tangents, NumPy tonnage, NumPy exponential, and axis flat is the second argument to zip, and then my colors. Then I can do this xplot. Axis, then the function I'm passing in. So this is each iteration, it's another function because it's iterating through all these functions. And for the color, I would like to use the color, which is also iterated. Oh, I see. I should call these colors. Okay, have a look at our figure. And as you can see, now we add these 6 functions with different colors. Yes, so I think that should be it for now, because Max also needs some time and we need also some questions. So this was a very, very basic introduction. Of course, your tab completion will always help you to find things. If you are stuck or if you don't remember, like, oh, how is set, blah, 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 what can I set exactly, then just type in set underscore and hit the tab. Or as I said, just browse the gallery, which will contain a lot of examples to do so. So this is basically it. I will upload, I already created a pull request where you also find a few other examples in this notebook, but those are not so nice compared to the Python, compared to the Matplotlib example gallery. So I recommend you to check that out. And now I would like to hand over to Max, who will show you how to take this to the highest level of styling.
Okay, so we saw some nice features of Matplotlib. Thomas showed them, and in the Git repository of the school, there is another directory. Let me just start sharing my screen and go into the repository. And I will switch back to the main branch and just update this with git pull. Okay, but the this part of the lecture is there already since quite some time, and this is called the Matplotlib publication quality directory. And what this lecture is about is that if you are writing a paper or a thesis, you want your plots to match the rest of your document. So you basically want your plots to look the same as the rest of your document. They should be fitting natively into your style of your document, and it shouldn't stick out that you're using a completely different font or font size for your documents. And we most probably all use LaTeX to write our papers and documents. So we want to also be able to use LaTeX really in our plots. So Matplotlib has a very nice feature set for this to really use LaTeX, our native LaTeX installation on our systems to produce not only the axis labels and so on, but also to insert formulas into our plots and to make sure that, for example, the fonts used here and the font sizes match our document. So you can observe here that our axis labels here are the exact same font and the exact same font size as the rest of our document. And this this plot basically fits very natively into our document here. And this part of the lecture will be about how to achieve this with Matplotlib, that we get our LaTeX styling, our LaTeX fonts into our plots and can then include our plots into our LaTeX documents. So I will just keep this open here. And then I have basically one version here before applying all these LaTeX styling. So this is a example plotting script using Matplotlib. Open it just with your text editor. We discussed a bit about text editors. I'm using Vim here, but for most beginners, you probably want to use something like Visual Studio Code. So I have this also installed. So let's just try this. Plot before.py. So this is now Visual Studio Code, and it also nicely highlights my Python code here. I can see the contents of my, yeah. So a great trick with VS Code is to not just open a single file, but open a whole directory. Either through the file dialog here, so open a folder, or through just giving it the path to a whole directory. And then you can see all the files in this directory here on the left side and can open one script here. And so we have some complicated LaTeX formula here. We use all this LaTeX stuff that Matplotlib supports. We have some power law spectrum. We do a plot with error bars. We add our X labels and our Y labels. We have here log10 of the energy in GeV and some particle flux. You may know these units from astrophysics. So we have a particle flux, which is basically number of particles per GeV, per second, per solid angle, and per square meter per area. And this now, if I want to store this as a PDF file, this will use the default Matplotlib styling. So let's just execute this plot before.py and look at the resulting plot. So this is this before.pdf in the build directory. And this is how it looks like. So we have a rather large plot, and we are using a sans serif font. This is, I think, the Déjà Vu fonts, which are the default on Linux. And the math looks okay, but I mean, this is not really what we are used to from LaTeX, right? This is some sans serif math, and it looks not as great as LaTeX, and it for sure doesn't match our document. So if I go back into this simple LaTeX file here, which is basically just a minimal header, and then this very simple document using this blind text, and I'm now including this before plot and not the final version I'm going to show you, and then run LaTeX on this document. And I want to not clutter my directory, so I will also store this output into my build directory. I will now have the, no, doesn't update. Let's check again. Oh, I have to give the option before the file name, I think. Yes, okay. So now let's look at this again. We have this very large plot and it's larger than our text area. And the fonts do not match at all the fonts we are using in our document. So what we can do using Matplotlib is to use the Matplotlib PGF backend. So Matplotlib has many different kinds of backends to export plots into different formats. It can store PDFs, PNG, SVG, and it can also create LaTeX code using, I don't know if you're familiar with the TIX package, but basically what Matplotlib can do is store the plot as a TIX code file, PGF code file, and use the LaTeX mechanisms to produce all these plots. And to achieve this, you write a config file for Matplotlib, and you can call this Matplotlib RC. So I have a Matplotlib RC here, which sets some options. So we want to use this PGF backend. And then I set the figure size here in inches. So Matplotlib needs to know the figure size in inches. And we will want to set this to our text width in the LaTeX document. And with an aspect ratio that's pleasing to us. So maybe 3:2 or 4:3 or the golden ratio, whatever you want. And then the question is, how can we find out how wide our document is so we can give the correct figure size to Matplotlib? And then we can also say, please use the text system, text.useText equals true. We want to do our own font management. And we want to use this modern Lua LaTeX engine to produce our plots. Matplotlib also supports using the other two modern engines, PDF LaTeX and XLaTeX. And we can set our own header file for Matplotlib to use. So in this header file, we will just basically put in all the packages we need for Matplotlib to set up our fonts and set up our math environment and so on. And then we can also set some font sizes. So these are the font sizes in our document. Our normal font is size 11, and then we make the tick labels a bit smaller so that the numbers at the axis are slightly lower. And we want to use the serif font, so the same font LaTeX is using for the main document and not the sans serif font, which Matplotlib is using by default for plots. How does our header look like? So this Matplotlib header. This is very simple. We just need to load the packages that are important for setting the fonts, which is here font spec, which can be used to set any system font. And then I load some math packages, ArmsMath, math tools. This package is very useful for typesetting units correctly. And this is also very useful here for setting the math font. So you can also, using this Lua LaTeX engine, you can use OpenType math fonts. Any math font you have on your system, you can then use with LaTeX. And in this settings file, this is a file I include with both the main document and my Matplotlib header. I just set which fonts I want to use. So just to make it different than the default LaTeX font, to really make sure that we are setting this, I use this Libertinos serif and Libertinos math fonts. We can also change that later to the default LaTeX font to see how it looks like with the defaults. And then I could change my plotting script to use all my LaTeX packages that I have now loaded. So for example, I can now use a text command that comes from ArmsMath, and I can use these Unicode math commands. So for example, Unicode math allows me to use really the Unicode signs in the math text, so I don't have to type this phi here, but I can just using my input system type the Unicode characters like this, which makes it much more readable. And then yeah, the rest of the plot is basically unchanged. I also use this SE unit X package to typeset my units here. So I use giga electron volts and the per GeV per second per steradian for this here. Yeah, that's basically it. So the plotting script doesn't change much. It's all about the configuration and the LaTeX header. And then I could now try to run this plotting script, but this will fail. So basically it says to me now that it cannot use these LaTeX commands. And this is because it doesn't actually load the config file yet. So for this, we can tell Matplotlib it should use this Matplotlib rc_pgf as a config file. And then we get another error that basically tells us that Matplotlib cannot find our header. And this is a bit confusing because, I mean, this header is right here. Why doesn't it find it? And the solution is because LaTeX is also creating these log files and these temporary files, and not only the output file. Matplotlib is kind of smart and runs LaTeX in a temporary directory. So in general, it will run this LaTeX command somewhere in /temp, and maybe we even find where I try to run it here, or maybe not. But the point is, you somehow need also to tell LaTeX where it can find your header from the temporary directory, and there's a tech inputs variable which you can give the current working directory and a colon, and then LaTeX will also find the header from the temporary directory. And you notice that this takes a while. So using this LaTeX backend is slower, but it results in really high quality plots, and to the effect that you have really the same fonts and the correct size and so on. And this is a trick how you can get the right image size for your document. So you can just into the LaTeX document, you can type the text width, and then in the document you will get the size in points. Then you just need to know that 1 inch is exactly 72.27 points, and then you can convert the number you get in points to inches, which is the unit Matplotlib needs for the font size. And let me change this back here to our plot.pdf. So we just include this, and we know that the PDF has a correct size because we set this in the configuration so that the plot is exactly as wide as our document. So we don't include any of these width or scale attributes here to scale it, but we just know that the plot is the correct size because we made it like this in the first place. Okay, so let's run the Lua, the main document again. And then we should have our proceeding back with a nice plot, which is exactly as wide as our document. Here is the output I told you about. So our text width is 418 point something points. And then I usually just use IPython to calculate this. So I'm sorry for the notifications. Let me just turn that off. Okay, sorry for that. Yeah, I will just copy this here, divided by the 72.27, and this gives me this 5.78, which I can enter in this Matplotlib RC here. So this is this 5.781, and then I divide it by 1.5, I think, to get a 3:2 aspect ratio for this plot here. Yes, and this is how it looks. So this is the way how you can use this LaTeX system to really get very, very high quality plots out of Matplotlib that really match the fonts and the style of your document you are writing. And we talked also a bit about these workflow automation systems. So in this directory, we'll also find a make file. You might not, I mean, you might not remember all these commands I just used, and it's also hard to tell somebody else. So I wrote a make file here, and make is basically, a make file is a set of rules how you can create your documents. So I say my targets that I want to create in the end, all I want to create is this preceding and this before plot. And then I have to tell make how to actually do this. So to create the preceding, I need as input the plot.pdf and this force, which I will explain later. And then I can call this LaTeX make command with the options I defined above here on the preceding, and that will create my preceding.pdf. To create the build plot.pdf, I need as input my configuration file for Matplotlib, the Matplotlib header, the settings.tech, and the plot.py, and this build directory. And then I need to give the same option you saw me give on the command line. So what is in this lower area here is basically called the recipe in make, and there you just have to input the shell commands you would have to type manually yourself to create the same thing. Plot before is simple. I just run the plot before. The build directory is created by just calling make dir build. And the clean is a nice convention to have in a make file that just removes everything the make file creates. So you have a clean state to start over. And LaTeX make is a very nice tool for LaTeX documents because it automatically runs LaTeX as many times as possible, as many times as needed, sorry, to create your document correctly. You might remember that you always need to call LaTeX multiple times to get like the table of contents and the reference to work, and LaTeX MK does this in the back for you, calls it multiple times. Will also call BibTeX or Biba for literature. So this is really nice to use in this kind of setting here. So, and when I do this, I can just make clean, and this will remove all the documents from this build directory and call make again. And then it will do in order all the stuff it needs to do to recreate this this document. And I only have to type make, and it will do all the steps in order and create the document. And you will see that LaTeX MK calls LaTeX twice to make sure everything is working here. And now if I do make again, it will basically say everything is already finished and it doesn't do anything. And now I can change, for example, we talked about the fonts. So let's change basically to the default fonts LaTeX is using. This is Latin Modern Roman and Latin Modern Math. And then I type make again, and make will realize that I changed an input file, and so it has to recreate all the steps that meet those input files. So it runs the plot again, and LaTeX make also runs it again. And now I have different fonts here. So these are now the Latin Modern fonts, but both in the text and in the plot, which is very nice to have this work out for both text and plot simultaneously, and using these workflow automation systems to create everything at once.
Very nice. All right, so we skip to the questions, I guess. Where is our chair?
The chair is not finding the mic button. Sorry.
Okay, I can also check the questions. Okay, so there are some questions already answered, I think.
Well, maybe you can. I think there was a good question that you answered, but to answer to everybody, what is why there is the figure and axis
Yes, of
objects.
course. Yeah. So maybe I'll start another Jupyter notebook. So the basic difference is that the figure is our whole area where we can draw stuff on. And the Matplotlib axis is one coordinate system, and you can add many coordinate systems to the same figure. And the figure is then what will be saved, for example, into one PDF file or one PNG file, and the X is what you actually use to plot stuff. So you can even use this Matplotlib notebook backend to get interactive plots in the notebook. So when I create a figure using plt.figure, I just get basically a blank canvas. And this can be used to draw stuff on. So now I can, for example, add an axis to this figure. And if I just do 1, 1, 1, this means I want to have one row, one column, and the first plot in this grid. So this adds me this coordinate system, which I can then use to plot stuff into it. Okay, so this will draw me a line, and if I add marker equals dots and line style is nothing, I will just get the dots. Okay. And then I can also say, okay, maybe I want to have two rows, one column, and the first plot of this. And then this X gets basically to half the size. And this is the one coordinate system I can use to plot. And then later on, or directly here, I can add one axis, and the second axis is the one number 2. And then I can choose what to plot into which axis. So I have the two coordinate systems, the one above and the one below. And if I now say that this should be color, I'm a fan of these XKCD colors. So let's choose the XKCD red. And then you see that the second axis, the one below, gets the red points. And the first one is the one above. And Tamas showed this really nice convenience method where you can basically get this all at the same time, which is this plt.subplots method, which will create the figure and the axis according to what you give it here for the number of columns and the number of rows. And you can then use this tuple unpacking here to directly get the two axis objects out from the NumPy array it returns.
Thanks. I think it's more clear and something that is confusing at the difference between figure and axis. So. There's another question which is not strictly Matplotlib, but I think it's an interesting one. What is the difference between import matplotlib.pyplot as PLT and from Matplotlib import pyplot as PLT?
There's actually no difference. So in the end, this will do. So if I understood you correctly, the question is whether to use this or this, right?
Exactly.
Yeah. So this will do the same, and this is shorter, so I always use this.
Okay, and there is no convention to use one rather than the other.
I think the Matplotlib documentation also uses this, so I would stick with this. But from the point of which code is executed, there's no difference.
Okay, I don't see any other generic question. Yes, one that I noted. Would you recommend Matplotlib for animation or suggest another package?
Matplotlib can do very nice animations. There's an animation package. I have actually some examples here. So maybe I just show you one I made recently. Maybe I just so I'm also giving a statistics lecture at the moment, and I made some animations for that. I think I called it like this. Yes. So this is an animation video I made with Matplotlib, which draws random numbers from a normal distribution here and from a Cauchy distribution here. And then we look at the mean and the standard deviation evolving over time, the more samples we draw from this distribution. You see that the for the normal distribution, this arrived at the true value, so a mean of 0 and a standard deviation of 1 after many. So it gets closer the more samples you draw, but the Cauchy distribution behaves strangely, and you have some weird behavior here. Yes, so there's this. What I use for this is this Matplotlib Funk animation. And this is very nice. It basically works. You give it a figure and a function that then needs to update the figure for each frame of the animation. I don't know if there's maybe there's a tutorial on this. Yes, so here's an example. So you define your figure, and then you define an update function where you basically do stuff. For example, I think here it just adds more points, and then you should get the update. So yes, it's very nice to use. It's not the fastest. Maybe there are other animation frameworks that are faster, but if you're used to Matplotlib, it's easy to also create animations with it. Yeah.
Cool. I like how I ask a random question and you have a you have an example prepared for that. Okay, well, I think that's pretty much it. I don't see any other general question. There is one that was just asked, the difference between Matplotlib and PyLab.
Oh yeah, that's one that comes up pretty often. So PyLab is a common namespace where there's stuff imported from NumPy and Matplotlib together. And I would highly, highly recommend to just not use it. Because it gets confusing, and you then even see people do from PyLab import star, and that gets you everything from NumPy and Matplotlib into the global namespace. This is really an historic artifact that was created to get MATLAB users to like the Python packages. And I think in the end, it did more harm than good, because people try to rely on it. So please just use NumPy and Matplotlib on its own and import the stuff from these packages, and don't use PyLab.
Okay, thanks. Then I think we can close the session now. We are a bit over time due to the break, but it's okay. So we stop here and we start tomorrow morning again at 9 a.m. With reproducible science in practice with Arturo. Thank you all, and see you tomorrow.